Okay, this is chapter 9 for physics, and in this chapter we look at static equilibrium, which is really the basis of the entire class in the engineering technology curriculum, statics. So although we could go into great detail here, we will not. This will just be a sort of a minimalist overview of the concept of static equilibrium. And then we'll look at elasticity and fracture, which is really a big component of strength of materials, which is yet another full class in the engineering technology curriculum. So we are essentially taking a full year's worth of potential topics and compressing them into one chapter. So as you can imagine, this will be somewhat abbreviated. So we have to go back to, first of all, remind ourselves of the idea of a normal force. So we talked earlier about an object sitting on a flat surface. Gravity is going to pull it in the downward direction. That is the force acting on the object. And gravity acts with a force equal to mass times acceleration, or mass times little g, when the acceleration is caused by gravity. Now, if the object is sitting on a flat surface and it's not accelerating, then that means that the object is pushing back against that force. It's perpendicular to the surface. That's where normal comes from. Normal meaning perpendicular. And that force is pushing back. So if we assume that there is no acceleration occurring, if this book sitting on the table is not accelerating downward or upward, then Newton's second law says the sum of forces equals ma. If a is equal to 0, then that means the sum of forces must also be equal to 0, which means that the normal force and the gravity force are canceling each other out. This cancellation is what we call equilibrium, static equilibrium. So it can be used to design all sorts of structures and mechanical systems in which forces are being applied, this idea, because we know that all of the forces are going to cancel out. Now, when we've got a book sitting on a table and the forces are all in the vertical direction, there's not a whole lot to it. Where it becomes a little bit more complicated is something like this, where we have a chandelier hanging from a cable that splits in two directions. We have a horizontal cable holding the chandelier to the side, and then this vertical, it's not exactly vertical, it's diagonal, but it has both a vertical and horizontal component to it. This cable A holding it up. So what we know here is that the sum of all three of these forces, the sum of these three vectors, will equal 0. Because otherwise, if it didn't, there would be some acceleration. So if we assume that the chandelier is not accelerating down to the ground and crashing or floating up into the air, it's just being suspended and it's remaining still, then that implies that these three forces cancel each other out. So these are two important equilibrium equations here. So all we're saying basically is that the sum of forces in the x direction, horizontally, all are going to cancel each other out. They will equal 0. And also in the vertical direction, all of those forces will cancel each other out. And so with that knowledge, we can then use some vector addition, some trigonometry, in order to find maybe some missing forces. For instance, let's look at this particular example here, where we have the chandelier that has a weight of 1,960 newtons. That weight is acting straight down because that's the way gravity works. It pulls things straight down. We have FB, the force in the rope that's holding it to the right, and the force in this diagonal rope, force A, that's acting up and to the left. It makes a 60-degree angle with the horizontal, which means that that angle right there is also 60 degrees. So I always like to say, engineers, we don't like diagonal forces. As soon as we encounter that diagonal force, we want to convert it into its x and y components. And so the way that we do that, if you'll recall, for the y component, we take the force, or the magnitude of the force, and we multiply it by sine of the angle, as long as that angle is with respect to horizontal, which it is. So FA sine of 60 is going to equal FAY. FAX, the x component of that force, is going to be equal to FA, the magnitude of that diagonal vector, multiplied by cosine of 60. Now, we don't know what FA is quite yet. Okay, that's one of the things we're going to need to solve for. So we can't really say much more than simply FAY equals FA sine of 60 and FAX equals FA cosine of 60. But we'll build on that. Let's go on to the next slide. So using those two equilibrium equations, I'm going to start actually in the y direction. Let's sum the forces in the y direction. The sum of those forces will equal 0. So what are the forces in the y direction? Well, we've got the weight of the chandelier acting down of 1960. So that's 1,960 newtons. And I'll make that negative because it's going down. What else is acting in the y direction? FAY is going to go up. And that's it. Those are the only two forces, because this FA, we've broken that up into the y and x components. Okay, so we can kind of ignore this because we've replaced it with these other two. So in the vertical direction, we've got the weight and FAY, and that's it. And FAY was FA sine of 60. And that is all going to be equal to 0. Okay, so we have our equation here with just one unknown, so we can solve for that. So FA is going to equal 1960 divided by sine of 60. And so this should equal 2,260 newtons. So that is the diagonal force we found, F sub A, right here and holding up the chandelier. Now to find the missing force FB, the force in that horizontal rope, we use our other equilibrium equation, that the sum of forces in the x direction equals 0. And what are the forces in the x direction? Well, we've got FB and we have FAX. And that's it. Those are the only two forces in the x direction. And so their sum must equal 0. So FAX is going to the left. So that's negative F sub A. And the horizontal component was F sub A times cosine of 60 plus FB. The two of those forces added together are going to equal 0. And so we know FA now. We solved that up here. So we can put that into this equation and solve for FB. So FB is just going to be equal to 2260 times cosine of 60. And 2260 cosine of 60 equals 1130. 1,130 newtons is the force in the horizontal rope. So that's an example of solving a system of forces using static equilibrium. And let's take a look here at the next slide. So we've said so far that the sum of forces in the x direction must equal 0 if a system is in static equilibrium, and the sum of forces in the y direction must also equal 0. But there is a third equilibrium equation, and that is the sum of moments about any point is equal to 0. Now, moments are a term that we use in statics class. Your physics textbook tends to use the term torque, which really means the same thing. It uses a tau for torque, and so we're going to, in this class, say the sum of torque equals 0. So a torque is caused by when a force acts at some distance. So if these two forces were applied to either end of the ruler, would the ruler remain stationary? No, probably not. It would probably actually spin about its center of gravity. And so even though the two forces might be canceling each other out horizontally, each of them are causing a moment because there is a distance d here. Force times distance gives us a moment, or torque. So although the sum of forces in the x direction might be 0 in this situation, the sum of the torque is not 0. So this is not an example of equilibrium. I think I'm going to stop this video right here. The software I use limits my video length to 15 minutes, and looks like I'm a little over 12 right now. I want to make sure that I can go through this next problem uninterrupted, so we'll pick up on example 9.5 in the next video.